Hello, this is Mr. Craig, and I wish to talk about bond energies, third law of thermodynamics, and Gibbs free energy. And I'm going to do a couple equations here, a couple examples. This is day 110, so let's go ahead and start with the first one here. It says, example number 1, calculate the entropy change for the reaction shown below. Assume that the reaction takes place at 25 degrees. Now, don't worry about the temperature just yet. We'll worry about that when we do some Gibbs free energy calculations, but that's not today. So you'll notice that you're given a table here. Actually, let's make sure that we're actually writing. You're given a table here that has some information for the reactants. And one thing that I want you to notice that's a little bit different from the table that we worked with yesterday was that actually oxygen has a value today. Because again, when we talk about entropy, we're talking about disorder, randomness, and oxygen gas has a lot of randomness and a lot of disorder associated with it. So it does have an entropy value, so you will see some values for that. However, do realize that this is a lot like the equation that we saw with delta H, and that this equation again is on your equation sheet, and it is, in this case, delta S is equal to the sum of the values for delta S for the for the products minus the sum of the delta S values for the reactants. So again, it's products minus reactants in this type of question. So what we're going to do is we're going to look at our balanced equation here. So we have two reactants and we have one product. So when we do this calculation, we'll do delta S. And again, we're going to take all the products, and we have two sulfur trioxides, and each one of those has a value of 256.7. And the units on this are in joules per mole Kelvin. Now, a little bit different. Now, don't worry about that unit just yet, because when we talk about Gibbs free energy and do some calculations with that, you're going to see some really neat things with these units. So don't stress out too much about that. All right, so that's all of our products. So now we'll take that minus the values for our reactants. And we have two sulfur dioxides, which has a value of 248.1. And again, that's joules per mole Kelvin. I'll kind of stack that up a little bit so we have room. Plus, we have one oxygen, so 205, and that's 0.0 joules per mole Kelvin, and so that takes care of that. So our delta S, when we take those values, type that in real quick, so 2 times 256.7 minus, use parentheses, 2 times 248.1 plus 205 gives me a value of negative 187.8, so we'll say negative 188. And again, that is our unit in joules over mole Kelvin. Now, don't worry about what that number means just yet. Okay, we'll talk about that in a little bit. I can't remember if I gave you values for delta S. I gave you values for delta G. I guess I can talk about it right now. When we talk about values for delta S, if delta S has a positive value, that means that it is an increase in entropy. It is an increase in the disorder of a reaction or the system. Now, we would expect this value to be negative because this reaction becomes more ordered. If you notice, we have, come on, right on that. So we have two particles, or two SO2s and one oxygen. So we have a total of 3 particles on the left side where we only have 2 on the product side. So we go from 3 to 2, so that's becoming more ordered. Therefore, the sign on delta S being negative is a good thing. We want that sign to be negative if our reaction becomes more ordered. All right, so I guess I'll talk about that more formally later on. I don't think I've talked about that yet in the lecture. All right, let's go to the next question. All right, so you're given a table here where we have bond energies, and these values will be given to you. So you'll always have these available to you. If you ever have to do some bond energy calculations, you'll have this information available for you. All right, now this question is quite interesting. And you know what? I am going to need to scoot this up a little bit. So I'm going to need my thing here. So let's Move that baby on down. Okay, so we'll flip back and forth, and let me see here. Get myself some more room here. We're going to need a lot of room for this question, so I apologize for not giving you very much room on this. All right, so example number 2. It says, using the bond energies from the table above, calculate the delta H for the reaction of methane with chlorine and fluorine to generate Freon 12. Also, we also create some HF and some hydrochloric. So that's okay. All right, so let's go back to writing again. Thank you, pen. Okay, so here's the first thing that we need to do when looking at a problem like this. Whenever we work with bond energies, we have to be concerned about the types of bonds that are being broken. If you look at this table that's given here, you'll notice that it's giving you different types of bonds and the energies associated with that. Now you'll notice that these are all single bonds. Here's some single bonds. Then we start to get into some double bonds here. In other words, you will not be presented with a situation that's not on the table. So if you say to yourself, well, I've got a hydrogen to bromine triple bond, I'm going to give you a heads up. That probably isn't right. Do be aware of formal charges. We do want to make sure that when we do these types of calculations and things that we do want to write our Lewis structures with the correct formal charges. So that's the first thing that we have to do because we're concerned about how many bonds or what types of bonds are being broken. So I want to write the Lewis structure. So looking at methane, carbon, and here's your organic lecture. Carbon will always have 4 bonds. And remember, hydrogen can only have a single bond because it can only have a maximum of 2 electrons. So here's our methane. Now let's go ahead and write the other ones. And again, if you need to do the formal charge calculations, please do that. Chlorine, again, will be a single bond. And one way to remember about chlorine's formal charges, if chlorine is an external atom, and in this case it is, if chlorine is an external atom, its formal charge will always be 0 if it has a single bond. In this case it does. So we have a single bonded chlorine here. The fluorines, same thing, it's in group 7A. So we have a single bond there. And we also have, we have 2 of those. Now, real quickly, formal charges. Formal charges deal with how many lone electrons you have and how many shared electrons. So when we do formal charges, we always want to do the assigned value first. So if you're doing the assigned value, and again I'll erase this here in a second, what we want to look at is how many lone electrons. So I'm doing it for this chlorine here. There's 6 lone electrons plus 1/2 of the shared electrons, which in this single bond there's 2 electrons. So that gives me a value of 7 shared electrons, or 7 total electrons that are associated with that chlorine. Yeah, I know it's got a single bond here, and technically there's 8 there. But when we do formal charges, we want to find out how many are assigned to that particular atom. And then doing the formal charge calculation, we take the number of valence electrons, and chlorine is in group 7A, so 7 valence electrons, minus the number that was assigned. If the formal charge is 0, everything is great. And again, all these formal charges should have a value of 0 because as I look at these elements here, there's no charges up here, so there's no ions. So all the formal charges should be 0 when we look at these. Let's erase that. Come on, erase. Really? Come on. Smiley face. Okay. Alright, so we're back. Let's go back to the drawing. So there's our structures, and now I want to draw it for the Freon 12. So again, carbon is always a central atom. Now, if you want to put your fluorines on opposite sides or in the next quad, it does not matter. Because again, once you spin this molecule, it's not going to matter. So there's our Freon. And then the HF, I'm going to scoot this down just a little. HF will look like this. Sorry if they're not showing all the dots here. There's 8 there. And then hydrochloric looks like this. So there's 8 dots around there. Okay, so now that we have all of our Lewis structures written out and drawn correctly with the correct formal charges, now we get to use the values that are in this bond energy chart. Now, recall from the previous example page that when we look at bond energies, that's delta H, BE, we're looking at the sum of the reactants. In this case, yes, it is reactants minus the sum of the products. So this is the one and only time that we take reactants minus products. All other times, whenever we do a calculation like this, it's always products minus reactants. So if you want to think of it like this, bond energies are like James Bond. Bond doesn't follow the rules, neither do bond energies. You got to have something dumb to remember this. All right, so bond energies don't follow that, so we want to erase this. Okay, there we go. All right, so now what we want to do is we want to find out all the bond energy, because what we're doing is we're going to break every single one of these bonds so that we can take these atoms and rearrange them to form new substances. You'll notice I've got methane, chlorine, fluorine. Over here I don't have any of that stuff. All the hydrogens have left the methane and attached itself to the HCl and the HF. So everybody's breaking apart and switching partners and doing all kinds of fun things. So here's what we need to do. Let's take care of the reactants first. So I'm going to do the delta H for the reactants. So how many bonds do I have on the methane? Well, I actually have 4 carbon to hydrogen bonds. So I have 4 carbon to hydrogen bonds. So I need to come over to my table and find carbon to hydrogen. There it is. So I have 4 of these, and it's in kilojoules per mole, right? Yep, there it is. Okay, so kilojoules per mole. So what I have is 4 times 473 kilojoules per mole. Okay. Then I'm going to add that to, well, I have 2 chlorines, so that means I have 2 Cl-Cl bonds that I need to break. So we need to find what the chlorine to chlorine is. And where are you? Man, my students were finding these really quickly today. There it is. So 239. 239. And that's kilojoules per mole. And I just noticed something here. That value is not 473. I think it's 413. Let me double check that. Yeah, 413. So let's stick a 1 in there. So put a 1 close. Alright, so now we've got our 2 chlorines and then the fluorines. And we have, I believe, 2 fluorines. So we're going to break 2 fluorine to fluorine bonds. So we'll have 2 times, whatever that is, fluorine. Oh, there it is. So 154. So we'll put that on there. And have this in kilojoules per mole. Okay, so there's all of our reactants. And I'm just going to do it like this, just to kind of clean things up. I don't have enough paper, or I should have done it landscape. But let me do this. So 413 plus 2 times 239 plus 2 times 154. So the total amount of energy that was used to break these bonds was 238, and that's in kilojoules per mole. Okay. So now what I want to do is I want to find the heat of the products. Now again, you don't have to do it this way, but if you look at my answers, click on the answers, that equation's like itty-bitty font, but it goes across the whole page. So this is another way you could do it. All right, so let's look at our products. We have our Freon 12 here, and we have 2 carbon to chlorine bonds. So let's go ahead and write that. 2 carbon to chlorine bonds. So I want to calculate that. Carbon to chlorine. Carbon to chlorine's right there, so 339. So I've got 339. And again, kilojoules per mole. And then I'm going to add that to, I've got 2 carbon to fluorine bonds. So 2 carbon to fluorine bonds, so 2 times whatever that is. Carbon to fluorine, 485. 485. Okay. And then, so that takes care of the freon. So now I have two HF bonds. So there, two of those. Two HF. So hydrogen to fluorine. Where are you? Hydrogen to fluorine, 565. That's a big one. 565. Okay. And then two HCl's. So two HCl. Oop. So two hydrogen to chlorines. So we'll go up. HCl right there. I kind of figured it out. 427. Alright, so let's do that calculation. Then we can do it real quick. Okay. So 2 times 39 plus 2 times 485 plus 2 times 565 plus 2 times 427. Okay. And that equals 3,032 kilojoules per mole. Okay, so what we want to do is we want to take the reactants minus the products. So we should get a negative value here, looks like. So I'm going to change that to a negative answer and then add it to 2438. So my delta H value, my bond energies for this reaction is a negative 1,194 kilojoules per mole. Okay, I'm going to be honest with you. This is not a very difficult task or a very difficult procedure, but it is tedious. I will give you that. But it is kind of fun, and I wouldn't be surprised if this were on the AP exam because it allows you to do some Lewis structures. I mean, we like doing Lewis structures, and if you draw them correctly, hey, life is really cool. And then there's another concept here that the bond energies are a little bit different than the other ones, that we do reactants minus products where everybody else is products minus reactants. Now the bad thing is that equation is not on the equation sheet. So you have to remember that when you look at the delta H for the bond energies, that it is the reactants minus the products. And you just have to remember that. I hate to say that, but it's the amount of energy of the bonds that are being broken by the reactants, and it's the amount of energy of the products being formed for those bonds. Okay, so let's move on to the next one here. That. All right. Example number 3 says calculate the standard free energy change for the complete combustion of methane at 25 degrees. So again, this is just delta G. So again, delta G is equal to the sum of the delta G values of the products minus the delta G value of the reactants. So this one's not too bad. We can deal with that. If I got enough room, let me kind of scoot that up a little bit. That'll give you a little more room here. Did it give us a little more room? Yeah. Okay. Oops. Pop that down. Okay, so now we've got some room to write. Alright, so let me go ahead and zap that baby. Oops. Yep. Okay. So it's products minus reactants. So again, we have our balanced equation here. So delta G is equal to, we have 1 carbon dioxide, and that has a value of negative 394, and this is in kilojoules per mole as well. We'll add that to, we'll add that to 2 waters. Oops. Add that to 2 waters. And water has a value of negative 237. And again, these are delta G values. Excuse me. And that again is in kilojoules per mole. Okay, so there's all of our products, and we'll subtract it from our reactants. 1 methane. So methane has a value of negative 50.8 kilojoules per mole. Now also remember that when we talk about delta G and delta H, they're in kilojoules per mole. The delta G values for anything in its elemental condition or state, again, it's still 0. So if you want to put it on there, that's fine. 0 kilojoules per mole. Okay. So then we get to do our calculation here. So box that all in. So delta G, do the calculation. So negative 394 plus 2 times negative 237.2. And a minus 50.8. So around a negative 818, I believe. Negative 817. We'll round that up. And that's kilojoules per mole. Okay. Alright. Going back to this reaction. Again, we have a negative G value here. What did I say earlier on about delta G? If it's negative, what does that mean? Well, if it's negative, that means it's spontaneous in that direction. And that's kind of a nice thing, because when we look at the equation here, this is a combustion reaction. So we would expect methane to react with oxygen to form carbon dioxide and water, because we know that does that. However, we would not expect carbon dioxide and water to shift in the reverse direction to form methane and oxygen. It will not happen. So again, delta G in this case here represents that it is spontaneous. In other words, a reaction will form carbon dioxide and water only in the forward direction. Okay, and we'll do some more calculations with delta G. Try this next one on your own. Go ahead and pause the video while you try to work this out. And don't listen to anything that I said until you've had a chance to try it out. Okay, so go ahead and hit the pause button here. Alright, now that you've had a chance to work this out, let's walk through it. One thing that I want you to recognize is you're only given 2 values. Why are you not given values for the iron and for the aluminum? Hopefully you realize, oh, aluminum and iron are metals at room temperature. Therefore, and they're also elements. So what kind of values should we have for delta G and delta H? A value of 0. So that's why you only see 2 values here. This makes this problem really easy once you do that. So our delta G, so again, products minus reactants, we have aluminum oxide. We have one of those, so it's a negative 1576.5, and again, kilojoules per mole. And then we'll subtract it from our iron oxide, well, our iron 3 oxide in this case, and that's a negative 740.98 kilojoules per mole. Okay. And when we go and calculate this out, do that real quick. So a negative 1576.5 minus a negative 740.98. And kind of ironically, we get another negative value. Now I'm going to ask you here, what kind of reaction do we have here? What is this reaction? Let me erase these so you can actually see what this is. And what kind of reaction do we have here? And we haven't done one like this in a while. This is going to try to replace that and kick that out. And it looks like it's doing that. Now, is this reaction going to take place? In other words, will the aluminum replace the iron to form aluminum oxide and iron? And don't say yes because I've written the balanced equation. Say yes because of what the value of delta G is, or say no because of what the value of delta G is. So delta G has a negative value. So will this reaction take place? In other words, will aluminum replace the iron to make aluminum oxide and iron? Hopefully you said yes. Why? Because of that negative sign. When delta G is negative, that means that the reaction in the forward direction will take place. And yes, the aluminum will kick the iron out. We'll see solid iron form in this. We'll see the aluminum bar disappear. And actually, not the next topic, but the topic after this, we'll do some electrochemistry behind this. It'll be pretty cool. So you get to do some redox questions here soon with these. So, yes, we would expect this reaction to take place. And again, that makes life very easy on us. Again, I hope this video has helped. If you have any questions, please don't hesitate to ask.